I'm going to be talking about coastal socio-environmental systems research through the lens of vulnerability and resilience. So it'll be a little autobiographical, but as we go through, it'll all coalesce. Just follow along. Born by the river that built America. So this is early Elliott, my little sister. So I'm born in New Orleans, roughly around that area. And it's very significant because being from this place has really shaped my life in many ways, obviously, but also has fundamentally shaped the science that I do. This is the house I grew up in. Shotgun houses are kind of a typical thing to see in New Orleans, and they're also kind of a sign of poverty. These is a form of housing that was cheap to build, easy to put up, and to get people in there to live, and this is where you house workers. And this is actually where my family still lives, so this is where I go home for holidays. But August 28, 2005 is a day that is very central to my life. So this is the day before Hurricane Katrina hit the city of New Orleans, and I put some highlights. So hundreds of thousands of people were asked to evacuate the city. Highways were jam-packed full of cars, and critically, those who were unable to leave many of them went to the ill-fated Superdome. And so this is my family's journey. We left on that day in a van that looked exactly like this, and we were driving to Galveston, where we have family. When you live in a hurricane zone and you're poor, you go wherever you can stay for free. And so for us, this was free. And so even though it took money to get there in terms of gas, we didn't have to pay for a hotel. It's normally about a 6-hour drive. It took us about 6 hours just to get to Baton Rouge, and it took us about 24 hours to get to Galveston. If you've ever been in LA traffic and you thought, wow, this is taking forever, this took forever, trust me. But yeah, we made it to safety, and safety in quotes. And the day we made it there, Katrina made landfall, and that's the day that my earth stood still, in the sense that, it's a day that I will never forget. And the next day is when news cameras were able to start to get in, and the aftermath of the storm was able to be seen. And this is satellite imagery. As you know, or as you may know, at the peak, about 80% of the city was flooded. Fortunately, my family lives over here, so our house wasn't flooded, but much of the parts of New Orleans that you're familiar with, so if you've been to City Park, the Superdome, Tulane University, the French Quarter was actually dry, but much of the city was flooded. And a consistent theme, if you were of age and watching the news at the time, is that the black and poor were left behind and left out. And some of this is graphic. There's a dead body floating in floodwaters, and people standing on top of roofs begging for help. And that's all kind of wrapped into this context of the city of poverty is just the norm in New Orleans. So I grew up in generational poverty, and most of the people I knew grew up in generational poverty. And New Orleans, I don't know if you all know who Ruby Bridges is, but that happened in New Orleans, and she came to visit my elementary school as a kid. So desegregation in the South did not happen with Brown versus Board of Education. It took a lot more effort to make that happen. And all the green that you see here are primarily black communities. All the blue are primarily white communities. And so this is the area I grew up in, and you can see it's like a white enclave, and my parents grew up in this neighborhood, and I remember asking them, like, why is that side of the street mostly white people? And they just said, it's the way it's always been. And kind of broadening the context from the socioeconomic aspects to the environmental aspects of southern Louisiana, looking at this image, you can see the iconic Birdfoot Delta. This delta is not naturally forming. It's a byproduct of environmental engineering. So all of the levees that we've put on the Mississippi River has all the sediment that comes from this giant watershed. Instead of spreading over the floodplains, all of that sediment gets shunted down into the Gulf of Mexico and creates this kind of artificial landscape. But all of the red that you see in this image are former wetlands that now no longer exist. It's all open water. And if you know anything about wetlands, you know that wetlands are natural defenses for storm surge with respect to hurricanes. And so you had 100 years of wetland degradation prior to Hurricane Katrina. And continuing on, climate change is a significant factor with respect to coastal communities in this area, in the South, but around the world. The rate of sea level rise in particular in response as a result of climate change is about 3.4 millimeters per year. Looking at this image, which I found out recently is no longer on the NOAA website. It's been taken down and replaced with a different one that is less descriptive of how bad sea level rise is. But if you look at southern Louisiana, the rate of sea level rise is about 3 times faster than any other place in the US and most places in the world. But in general, sea level is rising in all of these coastal places. And these things all come together for me and led to a research where I really wanted to think about wetland change and what wetland change actually means, what drives it. And I chose to focus on these coastal forested wetlands. Another word to use to describe them are swamps. So if you close your eyes and picture a swamp, you're picturing bald cypress trees, Spanish moss hanging. That's where I like to hang out. That's where I do my research. But these coastal forested wetlands are in decline across the US, and I'm going to go through that. And that decline is caused by salinization, so these are freshwater ecosystems. When they get salt in them, they eventually convert into salt marshes. And then these salt marshes are being eroded and becoming open water. And this is an image from the northeast of the US, where land is literally being calved off and falling into water. And people have done modeling work to show that wetlands are losing land, and the replacement is not fast enough. And so on the x-axis here, we have the current area of coastal wetlands and all the watersheds of the coastal US. And we have here the available land for wetlands to migrate into. And this is the one-to-one line. So if all of these dots were on the line, it's basically saying we're losing wetlands as fast as we're gaining them. But you can see most of the dots are below that line, meaning that we're losing wetlands faster than we're able to replace them, and most coastal watersheds are not able to keep up. And that's really critical when we start to think about humans in the context of these places. So sea level rise isn't just disrupting wetlands and their ability to function ecologically and within the environment. Sea level rise is also increasing the number of high tide flooding events. So looking at this figure in the top left, in 2019, there was a record in high tide flooding events, and high tide flooding events are the normal kind of tidal cycle, but because of sea level rise, the water level just sits slightly high enough such that when you have a high tide now, that high tide is a flood event, whereas 100 years ago, that high tide is just a high tide, your house isn't being flooded. And there's an increase in this trend across the southeastern US. And people typically think about sea level rise in a very specific context, but even places like Philadelphia are coastal. It's directly connected to water. And so these places that we tend to not think of as coastal are suddenly dealing with the impacts of sea level rise. This image from Miami is having a significant issue with high tide flooding events, and there's effectively no way to stop it because the geology is karst. Karst is just limestone. You can't stop water from coming into limestone and coming up. And so it's a significant issue, but people still have to deal with it. So this woman might be waiting to go to a pharmacy, go to a doctor's appointment, go to visit her grandkids. This person may be on the way to work, and they're just stuck dealing with these environmental problems. And in the broader context, we understand very clearly that the places where people are being affected by these things also overlap quite heavily with poor socioeconomic conditions. And so looking at some specific places, the more red the color is, or the warmer the color, the more there is a risk for being exposed to different environmental hazards. And so places like Houston, Southern Florida, the Bay Area, which even though we tend to think of the Bay Area as very wealthy, there's a lot of economic disparity in those places and vulnerability due to the effects of climate change. And so the way that I approach my science, I've tried to become more holistic in what I do and move past my training. And so all of my training is in environmental systems, but I do, as I kind of showed you all, there's a place-based understanding to what I do and the science that I've developed. And in addition to thinking about socioeconomic systems, to develop kind of my scientific approach, which attempts to kind of keep all these things in play at the same time and think about them in concert. So yeah, I was a field ecologist. I mentioned I spent a lot of time sticking my hand in the mud, hugging trees quite literally to measure them. And when I started my PhD, I had never operated a boat before, had not spent much time on the boat. By the time I finished, I was like the main boat guy and like taking the boat out. So this is on the Swanee River. Any of you have ever seen a sturgeon before or know what a sturgeon is? Okay, a sturgeon are these very large, kind of prehistoric-looking fish. They are prehistoric, and their body is basically armor-plated. It's full of like these hard, bony scales. On the Swanee River, they like to jump out of the water, and so you can be boating, going 30 miles an hour, and this big, bony fish may jump up and smack you in the chest. And so there are signs all over saying, "Watch out for jumping sturgeon." It's almost like something out of SpongeBob, but it's real. But I made this transition to doing a little bit less field work and focusing more on remote sensing. And I made that transition partially because in all the field work that I did, I realized geographically the spread of places I had gone to was very small. And doing remote sensing allows me to bypass some of the, not problems with field work, but some of the challenges that come with field work. So one, field work is extremely time consuming. It takes about 3 years to get a decent data set for ecology. And if you have something that happens bad at a field site, guess what? You might have to add on another year. And when you're trying to do a PhD in a finite amount of time, no one wants to be sitting there for 10 years for their data set to be complete. So it allowed me to kind of not necessarily accelerate my research, but do it in a different time span. Field work is expensive. It takes money to have a boat, to have a car, to put gas in that car and drive out there and do stuff. Permitting, this is a big one. Permitting is a political process in a way, and if the political organization that you're working with changes, they may limit access to certain field sites. And so maintaining permits is actually a pretty big concern in terms of access to places. You have to maintain equipment, which can be expensive. You need a lot of people to do field work. You have to maintain your interest a long time. Once again, to collect enough data, you have to be willing to sit in one spot for a while and keep that data coming in and wait maybe 3 years before you have enough to do any analysis. And then there's the geographic aspect. As I said, I had field sites across the Gulf of Mexico, but in actuality, the footprint of the places I was studying was relatively small. And it makes there are challenges within the field of ecology of scaling your results to places that you haven't been, where you don't know all the site-specific context, yet you want to kind of interpret your data in those contexts as well. And so I moved into remote sensing, something I had zero prior exposure to, but just taught myself how to do it. And centering around maps opened up a door for me that I hadn't thought about previously. And so you can take ecological data, and this is some of my work that I'll go over, take ecological data and socioeconomic data. In this case, this is from a paper showing counties that have above the national average in terms of percent of African Americans, and you can see a lot of these coastal counties have a greater percentage of African Americans compared to the average county in the US. But it allows us to co-locate data to maximize collaborations and access. And so with remote sensing, it's just a bunch of different data layers. And so you can take data about crops, water management, hydrology, demography, and really start to think about those connected in overlapping space and time. So my research group has two fundamental questions, and these questions are broken up between kind of pure natural sciences and the socio-environmental stuff. So the first question is, how are coastal land ecological integrity and continuity being disrupted by global climate change? And the second is, what are the inequities that marginalized communities face due to the impacts of global climate change? So we'll start out with the first one, and this is basically, I'll say, the first part of my career, which is capturing my doctoral and postdoctoral work. So this is from one of my field sites in near Beaumont, Texas, off the Neches River. This looks very pretty, and like you might be thinking, I'd like to go canoeing down that. We spent very little time in the boat. I would spend 8 hours basically in the swamp, where you're in water that's up to your knees all day. It's hot, there's mosquitoes. and there's basically no other humans around. And they're alligators, but I like all this stuff. So the North American coastal plain is this vast area that covers about 1.15 million square kilometers. It has been proposed as a biodiversity hotspot due to the array of ecoregions that you find that cover this area. And specifically focusing on the wetlands, there are about 6 main wetland types in this region. So you have mangroves, you have salt marsh, pine savannas, mostly in Florida and Georgia, riverine floodplains, coastal forested wetlands, and sawgrass. And just a small aside, sawgrass, the name is very fitting. It is this type of grass where if you rub your hand or run your finger along the edge of it from the tip to the base, nothing happens, but if you go the opposite way, it will serrate your skin. This picture is I'm standing on a boat. I have to get to a sensor that's deep in the sawgrass, and the only way to get in there is to just walk through it and get your skin ripped up. Field ecology is fun. Don't let me scare you away from it if you're considering it still. But despite this vast region and region both geographically and environmentally, there are multiple threats to coastal vegetation that span this whole region. So sea level rise, storms and tides, drought, water management, and connectivity. And these three are a little more obvious, so I'll only give these some explanation. Water management represents basically the way that people are shunting water on the landscape, extracting water, or stopping water from moving. And then connectivity connected to that is how have we augmented how water is connected on the landscape, so adding canals, et cetera, to move water to different places. But all of these lead to salinization in coastal environments, and this salinization has kind of myriad effects, but I'll get to that in a moment. So when thinking about saltwater intrusion in particular, we have to understand that it varies both over natural and is driven by both natural and anthropogenic factors, and it varies over both time and space. With respect to natural drivers of saltwater intrusion, the temporal scale is about over the course of kind of very acute events to the span of 1,000 years. And the scale that we typically think of these over tend to be regional, meaning a few states, up to globally. And so some examples might be hurricanes, which are like extremely acute events. You don't have 1,000-year hurricanes. That sounds like a post-apocalyptic hellscape. But hurricanes tend to only affect a few states at a time, whereas, let's say, subsidence and uplift, so these geologic processes take much longer time, and they also affect much bigger spatial scales. When we move to anthropogenic climate change, we're still looking at temporal and spatial scale, but the temporal scale has shortened, just representing the fact that we use fossil fuels to do things that give us a lot of energy and can accelerate how quickly we do things. And also the spatial scale is more limited because we can't kind of take an entire state and like dig up all the soil. That will be incredibly expensive. But some of these things might be land drainage, for example, where, if you want to put up a building somewhere and it's a little wet, you can get an engineering crew to drain that land in short order, but you're not doing that for an entire state at any given time, at one time, I should say. And so kind of coming back to this image from before, salinization affects all of these different coastal ecosystems, but the one that I focus on are these coastal forested wetlands. And this is, once again, from my field site in Beaumont. And for someone who does what I do, they can look at this image and know exactly what's going wrong. You all probably can't see it. But this tree right here is a bald cypress tree. It's my favorite species, including animals. I don't think animals are as cool as plants. But you have this bald cypress tree, and this image is taken in the summer when this tree should be kind of fully leafed out. All the branches should be green and vibrant and lush. But if you look at it, you can see there are a lot of branches where you don't really see any greenery. When you look in the foreground, you see a lot of brown. In the background, you see a lot of green kind of stuff growing out of the water. All of this brown stuff are cattail, and cattail do have a decent salt tolerance. However, it's relatively low. All of the green stuff in the background is sawgrass, and sawgrass is extremely salt tolerant. This tree species has a salinity tolerance, but it's fairly low, and I'll get to some of those details on the next slide. But or I should say not but when I see this image, I know that the groundwater here is salinized and that this is this ecosystem under stress. And it's important for me to contextualize what I mean by salinization for my ecosystem. So when you're in a low or 0 parts per thousand ecosystem of this ecosystem, when you look up in the canopy in the summer, you should see like a fully enclosed canopy, not many gaps in the canopy. But as you increase the salinity of the groundwater, you go into this state that we call the ghost forest, and I'll talk about that more on the next slide. And eventually you start to shift into something that's basically adapted to being in salt water. And to put in perspective what I mean by salinity, or not salinity, but the limits that we're talking about, fresh water is considered anything below 0.5 ppt or parts per thousand. Part per thousand is equivalent to a gram per liter. Ocean water is about 30 to 35 parts per thousand. So if you take a liter of water, put 30 grams of salt in it, and drink it, you might as well be drinking the Pacific Ocean. I mean, it's going to be cleaner than the Pacific Ocean. This transition into a ghost forest, which represents like basically the final stage of degradation, starts to happen around 2 parts per thousand. So it's not even like you're getting full strength ocean water to make this happen. That's how sensitive some of these species are to salinity. So ghost forests are not like haunted places, but they are very scary if you understand what it takes to cause this type of conversion to happen. And so these ghost forests, I call them sentinels of climate change. Groundwater salinization is not something that you can just go and see. You can't just look at it with your eyes. There's no color difference, really. I mean, you can use certain instruments and maybe get some color difference, but mostly it's no color difference. But it's called a ghost forest because when you look at this, you see all of these gray things standing up. These are dead trees that died some time ago. But it's quite clear that in order for this tree to get to this height, it had to be living in this place for a long enough time in good enough conditions. And so it's representing that this used to be a forest that was healthy and vibrant. The environmental context has changed, the abiotic conditions have changed such that this tree can no longer survive here. And so I tend to think of these almost like graveyards, with all of these dead gray trees being tombstones of a forest that once was, that will never be, similar to people that are in graveyards. And so research from my postdoctoral work, we showed that we've lost about 13,000 or almost 14,000 square kilometers of this ecosystem in just 20 years in the US. That's 20 years. And most of this is clustered in the southeast, primarily in Georgia, North Carolina, South Carolina. And to put this number into context, because that may not mean much to you all, how many of you all have seen a mangrove before, a mangrove forest? How many of you all have paddled through one? Okay. Mangroves are found all over the world. A paper came out just before ours did that looked at mangrove loss around the world. Over roughly the same time period, we only lost about 3,000 square kilometers of mangroves globally. In just the US alone, in about the same time period, we lost, obviously, multiple times that. However, you probably haven't heard about this problem, but I'm sure you've heard about, like, don't cut down mangroves, they're beautiful. And so I think part of my job is to be an evangelist for this ecosystem to make sure people understand that it's something we should protect and that it's being lost right under our eyes. And not only did we kind of identify how much has been lost and quantify that, but we also want to go a step further to understand what's actually driving that loss. And so a very extremely simple linear regression using only a handful of factors was able to explain 78% of the variation in wetland loss, of this particular wetland loss across the US. And even when we had a model that dropped some things out, these 5 variables still captured basically everything. And we want to go another step forward further to actually figure out when this ecosystem does transition, what does it transition into? Most people tend to think of when you lose a wetland, it goes into open water. However, we show that it only happens about 2% of the time, and this is a pretty rare sight to see. This is from coastal North Carolina. Historically, urbanization and agriculture has decimated wetlands across the US and really across the world. When you think about where agriculture was started, Mesopotamia, those floodplains are wetlands, and wetlands have very rich soil. So wetlands have been exploited for their rich soils throughout human history, including in the US. Much of the Midwest of the US, where we produce all this agriculture, used to be wetlands that we drained, getting back to kind of threats to wetlands. But presently, that's only about 9% of the loss that we're seeing. Most of the loss that we're seeing is following this degradation pathway that we understand from decades of fieldwork, so fieldwork is extremely valuable, where you go from this thriving ecosystem into a ghost forest. Eventually you get kind of freshwater plants and then eventually saltwater plants, and then finally open water is the final stage in most contexts. So thinking about another component of this that we really wanted to tackle was, how is this like spatially changing over the landscape? So this red outline area here is Palmetto Pear Tree Reserve in North Carolina. It's protected land. People aren't doing any logging on it. Everything you see that is green is forest, gray is non-forest, 1996. By 2017, you see a lot of gray, and a lot of it's in coastal, right near the coast, so you may be thinking, oh, that makes sense. But if you actually pay attention to regions like right here, which are much further inland, are losing forests, and so this is that same region. And then you start to think, what's driving that? And what's driving that is the way that we have altered the hydrology of most coastal systems, where we're adding canals, we're adding ways to manage water. And in these coastal plains regions, you have very shallow slopes of the landscape, and so a lot of it's just pure gravity drainage. But guess what? That kind of balance changes with sea level rise. So now, because this is your gradient, as the sea level rises, salt water is going this way, and then it's going that way. And so our alteration of the landscape has led to this outcome where we're getting die-off and salinization of forests, leading to die-off in places where we didn't think it would be happening, because we always thought it's only happening right on the boundaries. But now it's happening a lot further inland than we ever thought. And that's really critical as we think about climate change and how we're trying to mitigate that. We know there's too much CO2 in the atmosphere, and the planet is telling us that by kind of trying to increase the temperature and cook us out. But this ecosystem holds a lot of biomass. And when you have this transition, you end up with a system that can't hold as much biomass, but yet it's still taking up a lot of land. And so some of that biomass is actually being respired back into the atmosphere because you're getting a change in the soil biogeochemistry, which is creating additional issues. And there has been increasing mainstream attention to ghost forests over the years. New York Times, Science Friday, and a bunch of different publications. And this title right here from CBS News, Ghost Forests, What They Are and Why They're Becoming More Common, could have been the title of my dissertation, but as scientists, we were kind of stuffy at times, and we can't have nice titles like this. So yeah, that's the end of that chapter with respect to some of the natural sciences work that I do. And so I went through this kind of critical transition point. Well, these are my parents, my mom, Linda, my dad, Elliott Sr., and this is from my PhD graduation. But my time as a postdoc was, I think, very critical to my identity in many ways, as a scientist, but also as a person. So my postdoc started in January of 2020. I moved to a new state, a new institution, and was on campus for 3 months before I was actually away at a funeral, and I got an email saying, "Don't return to your office." I'm like, oh, okay, well, hopefully it won't be too long. And I spent the rest of my postdoc working from my kitchen table, which sucked. But also 2020, for I think many of you in this room, is a very eventful summer. I'll just kind of leave it in those terse terms. And my postdoc was at the University of Virginia in Charlottesville, which was kind of made national news in 2017 because of a lot of hate. And so I find myself in a situation where I'm being a scientist, but I'm being confronted with social problems in a way that I think people in my generation hadn't had to contend with. I was really afraid of COVID, so I didn't go to any protests because I just didn't want to get sick. But what I did was I went to Lowe's once we were able to go in stores, and I just bought these poster boards and made my own sandwich board and just walked around Charlottesville by myself, silent protesting. So these images, somehow CNN got news of this, and I got interviewed with several other people from around the country. This right here is the first time that my science made the news, and so this is me out with an NPR reporter in coastal Virginia talking about ghost forests and salinization, so that was cool to know that people are interested in what I do beyond just the people that I see at conferences. And that brings me to this kind of transition point in my career where I really start to bring the social components back in. And so the second question that my research group really focuses on is, what are the inequities that marginalized communities face due to the impacts of global climate change? So this is a place called Manatee Springs in Florida. The water level normally isn't this high, and my wife is the one who took this picture. My wife is not a scientist. She's not really an outdoors person, but I needed someone to come with me for field work that day, and on this day the river happened to be at flood stage, and so she tried to follow me for a little bit, and eventually I turned around and said, just go back, please. I feel more comfortable going out there by myself than worrying about you. This water is about knee deep, and I'm pretty tall, so it's about 2 feet deep. It's the color of really dark tea, so you cannot see what you're walking on or but I've spent hundreds of hours in these places, so I'm pretty sure-footed. So once again, field ecology is pretty amazing if you're up for it. And so when I took my job at Stanford, I saw this as an opportunity to I got a different sense of independence with respect to the research that I can do. And I threw myself headfirst into these community-focused projects in a way that I sometimes think was probably a little haphazard, but I was happy to be able to do whatever I wanted to do with respect to my research. And so these are all community kind of focused projects that I've launched since I started in 2022 from a bunch of different funding sources and partners. So one of our projects is actually with the city of New Orleans, which might be one of the most kind of prideful things I've ever done as a scientist, to contribute back to a city that's given me so much. So I'll focus on only a couple of these. The first being using machine learning. I know next to nothing about machine learning, but I know how to find people that do and work with them to help me do stuff. And so really thinking about how can we use all of this environmental data to enable the use of nature-based solutions to do good for the world. And so there are all of these different kind of environmental data sets that we were able to scrape together in order to, with the goal of producing 3 different outcomes. One being a presence map for coastal forested wetlands, another being a habitat suitability map, and the third being a map of all the carbon that this ecosystem holds. And just kind of recognizing my audience, a presence map is just, is this thing here or not? Habitat suitability is not about whether it's there or not, but whether it could be there or not, whether the environmental conditions could support it. And then the carbon stock map, I think that one's more straightforward. So this is the team that I pursued this with. And what we're able to do, so I'll step you through this. These are raw images from Landsat. So Landsat, if you've been over to JPL, that's where they build these satellites. Landsat is a USGS, US Geological Survey, and NASA joint mission to produce satellites that take images of the planet from space. This has been going on since 1972, and it's the longest record of observations of the planet's surface in human history, obviously. And so we had training data of where these ecosystems do exist, and so these are our ground truth. And then we trained Inception ResNet version 2. I can try and answer questions about this, but don't press me on it. And our model actually did pretty well. And for those of you that do machine learning, you know you need large data sets to do it effectively. There's no pre-tagged data set for this ecosystem. We were basically working on my knowledge of where this ecosystem can exist. And so it did pretty well, and I've spent a lot of time looking at this map, and I understand what the flaws are, but those flaws are things that currently can't be mitigated with the data sets that we have. But the overall takeaway is that the model performance is good. It's able to capture kind of the large features on the landscape, but it does poorly with the more detailed aspects. I think that's okay given the scale of the challenge that we put in front of ourselves. And then next, so this is kind of that model applied, or this is actually the habitat suitability map. And so the darker the blue, the more likely it is that this ecosystem could exist there. And this isn't the greatest image, so I apologize for that, but you'll notice that it's mostly in these river corridors that you find this ecosystem, which makes sense. And there's some flaws that I recognize that you can ask me about later. And we also, so this was just using a random forest, so not as high powered, want to understand what are the features that are important for predicting whether this ecosystem could exist. And we didn't want to include only kind of geographic features and things like slope and elevation. We also want to take into account environmental conditions, because we know that those will change due to climate change. And actually, the output here is using climate predictions for the year 2050 and including sea level rise to understand what this ecosystem will exist in the next now 25 years. And that part is really critical because we wanted to do community engagement with this, and the community engagement was really centered on how can we think about this ecosystem as a nature-based solution to prevent flooding. And so understanding where it could exist means that we're not just limited to where this ecosystem currently exists and connected with those communities, but we can start thinking about reforestation in places where this ecosystem maybe used to exist but now no longer does. And so here's a team that's driving that work forward, and just maybe as a moment in time snapshot, this work is funded by the USDA Forest Service through a small grants program that's focused on getting small-scale landowners to basically make their land financially valuable for them. Our grant was frozen for a while by the new administration, but it has recently reopened. And what we are doing is using this map, using our output, so all of the gray are areas where it is 75% probability or higher that this habitat is suitable for these forested wetlands. And the green are IRS opportunity zones. I was the one who suggested using this, and so then I had to read all about it. But IRS opportunity zones are basically places in the country where the IRS has said economic, a financial injection of money into this place is needed to kind of bring up the well-being of the people, and there are tax incentives for businesses to go to those places to do businesses. And so from the reason that I picked this approach was because it was something standardized that we didn't have to define the community that we want to work with. It was predefined by the government. We're actually piloting this project in Prairie View, Texas. If any of you know what HBC, all of you should probably know what HBCUs are. I'm not always in front of an audience like this. So we're partnering with Prairie View A&M and trying to help that community of small-scale landowners get some economic value from their land that doesn't force them to destroy their land, do some type of other extractive industry. My next project that's really community focused is in Houston. So Hurricane Harvey nationally has forced conversations about should we be thinking about 500-year floodplains. How many of you know what a 100-year floodplain is? All right, this is actually disconcerting. When you have some free time, maybe tonight, look it up. And this is really critical. All of these houses most of them were built within the 100-year floodplain. And the 100-year floodplain is what FEMA uses to decide who needs to have homeowners insurance, or not homeowners insurance, who needs to have flood insurance. Only the federal government provides flood insurance because it's incredibly expensive and no private company wants to take that on. And so if you live in a 100-year floodplain, you have to have flood insurance. And if you don't, you are screwed because there's no one else that will help you. Houston went kind of out of control in terms of development. It is a place with basically no zoning laws. So if you ever go to Houston, you'll see things right next to each other that you wouldn't see in any other places. But in particular, they were just building houses in floodplains and not telling people. So like most of you don't know what a 100-year floodplain is. You might buy a house. Yep, this is where we're going to spend the rest of our life. And then you get flooded, and then someone tells you, oh, actually, you live in a floodplain, and you didn't know. So that's why it's important to know what a floodplain is. This is all publicly available, so look it up. But what happened with Hurricane Harvey, it produced more rainfall than we are used to experiencing from hurricanes, and it just sat over that area for a long time, just dumping rain for days, really. And people who even weren't in the 100-year floodplain were getting flooded, and it then, through kind of the meteorologists out there, did some analysis of the rainfall patterns and said, like, this is a 500-year storm. And I probably should talk about what a 100 or 500-year storm is. This is basically the inverse probability. So it's effectively saying, in a given year, what is the probability that you can expect a storm of this magnitude? So I think for a 500-year storm, it's like a 0.02% chance of experiencing that storm in any given year. So it's a rare event. So that's why it's 500 years. Once every 500 years, you might expect something like this to happen, but it happened. And now there's intense work being put into, is the 500-year storm that we used to think about actually now a 100-year storm, and do we need to actually redo all of our flood maps to expand the boundaries of what we normally thought about? But these images probably remind you of something from that I showed earlier, Hurricane Katrina, of mostly poor black people kind of dealing with the effects of this storm. And to be, not to give you a biased perspective, the city of Houston is extremely diverse, and a lot of people were affected by the storm in terms of the demographics. But work done post-storm showed that poor and people of color got fewer resources to help their recovery compared to other communities. And so there's still disparities, even if it wasn't on the impact side, the disparities on the recovery side persisted. And so this event, even though it happened in 2017, and I didn't start my position until 2022, was in my mind. And really getting into these nature-based solutions perspectives, I started to think about, can nature-based solutions be an effective strategy here? And that's, I think, really important because most of the time when we think about how do we stop flooding, we immediately go to great infrastructure, levees, dams, pumps, et cetera. And there was a poll done over several years after the event, asking people, well, what type of things would you like to see the city do to prevent these types of events? And if you look at these, none of these are nature-based solutions. None of these talk about returning greenery back to the environment as a way to prevent flooding. And in the greater Houston area overall, you've had this massive shift away from wetlands into developed land, into open water, and the return on wetlands over the same period is much smaller. Wetlands do an amazing job of holding water and preventing floods. That's why typically people didn't live in floodplains, because they get flooded, but guess what? The flood stays there and it doesn't come where you live. But Houston, as I said, kind of went crazy in terms of development and just destroyed a lot of the wetlands. And if any of you are from the South or from Houston, you might know that the nickname for Houston is the Bayou City. A bayou is just another type of wetland. But if you go to Houston, you don't see many wetlands. They have all these places that are called like Greens Bayou and stuff, and those are still wetlands, but the landscape is significantly altered to what it used to be. And so this team of folks, Stanford scientists, and partner with a community organization to really think about, one, not only how do we implement nature-based solutions in this area, but how do we actually bring the community into this conversation? I didn't want to do science in a way that I am prescriptive in what I do and say, and just sit at Stanford, do some modeling, and, oh, all right, here you go, this is what you all should do. No, we actually want to bring the community in and get their perspective. One, do they even understand what nature-based solutions are, and do they have any buy-in in this? Because we wanted this to be a more grassroots efforts of producing data for communities that they can use to then go to their council members, their politicians, and say, hey, this is the data that we've got from working with these scientists. Why aren't we doing this? This is what we want to see in our communities. And so going a little bit more detail, we worked with 2 specific communities in this area, so Northeast Houston and Baytown. Northeast Houston is a primarily impoverished Black community. Baytown is a primarily impoverished Hispanic community. And specifically what we were thinking about is, are there ways for us to, and maybe I take a step back about what flooding is in urban context usually. So in an urban context, a flood usually means that there's more water than the landscape can hold, but because we live in cities, we don't want to deal with floods, and so we have extensive stormwater drainage networks. And these stormwater drainage networks shunt water to the nearest stream as fast as possible, but I'm really realizing my audience in terms of discipline. There's something called a hydrograph, essentially, and it's basically how much water there is per unit time. If you put too much water in per unit time, the system can't handle that, so then you get a flood, it overflows. And so we want to think about what are ways that we can capture water upstream of these communities. So these are the communities, this is the upstream. What are ways that we can capture water and hold it there for longer time such that the peak of this hydrograph is not as high, meaning that you're less likely to have a flood. And so that's the way we went about doing it. And we had this design scheme where we restored different amounts of wetland on the landscape. We gave the landscape different amounts of rainfall, so a 1-year return storm, a 100-year, and a 500-year. And we went down to Houston and talked to communities. This is my very first time being part of a focus group. One of the more exciting things I've ever done, and I've seen like manatee and alligators and stuff, and dolphins. This was much more exciting to hear people talk about their problems, to capture that, and to give them a way to talk about their problems with others who have the ability to make those changes. And so this is some of the modeling results. The more blue the color is, the more flooding there is on the landscape. At the top, we have the baseline, so what the current landscape is like in terms of land cover and land use, and at the bottom, we have where we restored wetlands. And the columns are the different design storms going from lowest intensity rainfall to highest. And you'll see that in the baseline, more rain means more flooding. But when you have wetlands in the landscape, more rain means more flooding. But compared to the baseline, we have less flooding overall. And that's the main takeaway here, is that you bring wetlands back to the landscape, you reduce flooding, you remove or reduce the number of people that will be impacted by flooding. And we want to go a little bit further to give them a restoration prioritization metric. That's a mouthful. But we want to look at the opportunity for restoration and the benefit for restoration. And we identified these 3 watersheds as places that we should prioritize for restoration because the opportunity to benefit ratio is just much higher than many other places. All right, coming to the end here, this is all my doctoral students, so 2 PhD candidates and 3 second-year students and 2 first years. And for us, community engagement is a value, not a theme. We're not doing it kind of haphazardly and like, oh, this is a fun time to do it. Like it's a real core part of the research that my group is doing. So looking at forestry and indigenous values, wetlands and cultural practice, equity-based flood mitigation, water resources and community engagement, and saltwater intrusion and environmental degradation. So to bring it all back home, the research I do is coastal socio-environmental systems research that really attempts to integrate environmental systems, capturing place-based experiences, socioeconomic systems, and coalescing all of that into a way to think about them in concert. This has been in my slides since I started giving job talks. Continue to diversify the sciences. Progress takes sustained effort. And maybe the last thing is you have a voice that should be heard, and make sure it is heard. This is an opinion piece I wrote in the Stanford Daily, basically calling out the university's silence on the attacks on minorities and science in general. Thank you. I no longer exist on any social media. I deleted that months ago, but you can email me or go to my website, coast.stanford.edu. This is my group, and we're all praising my daughter. She's our mascot. Thank you.